Previously, we considered two linear equations and how to solve them. We saw three methods. The elimination method, where we added the equations together to eliminate one of the variables. The substitution method, where we solved for one of the variables in terms of the other and substituted it. And finally, we saw the graphical method, in which we graphed the two lines and looked for the point of their intersection. In this class, we'll consider more general equations of two variables that do not necessarily both need to be linear. For more general equations, there's no elimination method that's useful for solving them, so instead we're going to have to use the substitution method or the graphing method, or both. Suppose we want to solve two equations, x plus 2y equals 1 and y equals x squared. We'll use the substitution method here. Since y equals x squared, we can substitute x squared for the y in the first equation to get x plus 2x squared equals 1. Now we have to rewrite this in normal quadratic equation form by subtracting 1 from both sides and putting the x squared term at the front, giving us 2x squared plus x minus 1 equals 0. We can solve this using the quadratic formula or solve it using the factoring method, and we will end up with a response that x equals negative 1 or x equals a half. Those are the 2 points at which you're going to have intersection between these two shapes. Now, if we substitute those values into either equation, we can see what the y values are. Let's take the second equation since it's easier, y equals x squared. If x is negative 1, then y equals negative 1 squared, or 1. And if x equals a half, then y equals a half squared, or a quarter. Therefore, our first solution is x equals negative 1, and y equals 1, or 1, 1, negative 1, 1. And our second solution is x equals a half, and y equals a quarter, or a half, a quarter. These are the only two solutions. Let's look at how you would solve this equation graphically. X plus 2y equals 1 is a straight line, and y equals x squared is a parabola. When they are graphed, the intersection points are what we're looking for. And as you can see, they intersect on negative 1, 1, and 1 half, 1 quarter. Let's use another example and solve the equations y equals x squared plus x and x plus y equals 3. We'll use the substitution method. Let's start with the equation x plus y equals 3 because it's easier to use it. We solve for one of the variables, say x, by subtracting y, and we get x equals negative y plus 3, or 3 minus y. Now we need to substitute this into the other equation of y equals x squared plus x. Since x equals negative 3y, we get y equals 3 minus y squared plus 3 minus y. Here we open the parentheses by expanding 3 minus y squared into 3 minus y times 3 minus y, which, using FOIL method that we discussed earlier in the course, becomes 9 minus 3y plus y squared. The overall equation is now y equals 9 minus 3y plus y squared plus 3 minus y, because that was what the x term substituted into. Once we combine like terms, we get y equals 12 minus 7y plus y squared. This is a quadratic equation. In order to solve it, we can bring it into standard form by subtracting y from each side and putting the squared term, so that what we end up getting is y squared minus 8y plus 12 equals 0. We can use the quadratic formula, or we can factor to get the answer. Either way, we get the answer as y equals 2 and y equals 6. Now substitute this into either equation, say x plus y equals 3. So for y equals 2, we see that x plus 2 equals 3, which means that x is 1, giving us a solution set of 1, 2. If we substitute y equals 6, we see that x plus 6 equals 3, which means that x is negative 3. Giving us a solution set of negative 3, 6. So, the solutions are x is 1 and y is 2, or x is negative 3 and y is 6. Here is the graph of these two equations and where they intersect. From the curves, we see the 2 points of intersection are 1, 2 and negative 3, 6, which are the points that we got when we solved the equation algebraically. Now let's take it up a notch and use it when you're talking about both quadratic equations. Let's look at this example. Let's solve the equations y equals x squared plus x and y equals 4 minus x squared. Here, in the first equation, the y variable is already solved for in terms of x, so we can simply substitute x squared plus x for the y in the second equation, getting us x squared plus x equals 4 minus x squared. This is a quadratic equation, so we have to bring it into quadratic form. Add negative 4 to both sides, and then x to both sides, and x squared to both sides. So we end up with 2x squared plus 2x minus 4 equals 0. Again, we can solve this using the quadratic formula or factoring. We can factor 2x squared plus 2x minus 4 into 2x minus 2 and x plus 2. So we have 2x minus 2 times x plus 2 equals 0. On the left side, we get 2x minus 2 equals 0, which makes x equal 1, and on the right side, we have x plus 2 equals 0, which means x equals negative 2. If x is negative 2, based on the original equation, then y equals negative 2 squared plus negative 2, which is 4 minus 2, which is 2. If x is 1, then y equals 1 squared plus 1, which is also 2. Therefore, x equals negative 2, and y equals 2, or negative 2 is one solution, and x equals 1 and y equals 2, or 1, 2, is another solution. Again, by graphing both of these parabolas, we can see those as the point of intersection. Consider the equations y equals x squared minus x and x minus y equals 2. If we solve the second equation for x by adding y to both sides, we find that x equals 2 plus y. Now substitute this into the equation, y equals 2 plus y squared minus 2 plus y. Expand the right side using FOIL on 2 plus y times 2 plus y to get y equals 4 plus 2y plus 2y plus y squared minus 2 minus y. Eventually, the equation simplifies to y equals 4 plus 3y plus y squared. Now subtract y from both sides to bring it into standard quadratic form, and we get y squared plus 2y plus 4 equals 0. The problem is we cannot solve this equation using factoring or the quadratic formula. If we apply the quadratic formula, we see that we get negative square roots. So this quadratic equation has no solutions. We can also see it quickly by looking at the discriminant. The discriminant here is 2 squared minus 4 times 1 times 4, which is 4 minus 16, which is negative 12, which is negative, hence there are no real solutions. Therefore, there are no numbers for x and y that satisfy the equations y equals x squared minus x and x minus y equals 2. If we graph the parabola and the line, we'll see that in fact they never intersect. There are no solutions to this system of equations. There are many different variations on this theme. Two parabolas may intersect at one point, in which case the two equations have just one solution, or they can intersect at no points, in which case the equations have no solutions. A line on a parabola can touch each other at only one point, and so forth. Let's take a look at an interesting example. Let's solve x squared minus y squared equals 2, and x plus y equals 1. You may be wondering what kind of curve x squared minus y squared equals 2 is. It doesn't matter, because we can still solve these equations algebraically. It turns out it's a hyperbola, something that we haven't covered in this course, and we won't cover it in this course. It doesn't matter what the graph actually looks like, the procedure is the same. Solve the second equation, x plus y equals 1, for, say, x, meaning x equals 1 minus y. Substitute the 1 minus y into the second equation, giving us 1 minus y squared equals 2. Use FOIL on the first expression, and the equation becomes 1 minus y plus y squared minus y squared equals 2. This simplifies to 1 minus 2y equals 2. Subtract 1 from each side gives us negative 2y equals 1. Divide by negative 2, and y equals negative 1/2. Substitute into the other equation, x plus y equals 1, gives us x minus a half equals 1, meaning that x has to be 1.5. So there's only one solution to these two equations. X is 1.5, and y equals negative 0.5, or negative a half. As before, we can use these methods to solve word problems and puzzles that lead to a pair of equations. Let's look at an example. A rectangle has a perimeter of 16 feet and an area of 15 square feet. And let's say we want to know the dimensions of the rectangle, the length and the width. Let x be one dimension, again doesn't matter which one, and let y be the other dimension. The perimeter is all the dimensions combined, or x plus y plus x plus y, and that equals up to 16. So 2x plus 2y equals 16. The area is 15, so x times y equals 15. So we've now got a system of equations. 2x plus 2y equals 16, and x times y, or xy, equals 15. Let's solve this by substitution. Let's start with the first equation, 2x plus 2y equals 16, and solve for one variable, say x. Subtracting 2y from both sides, we get 2x equals 16 minus 2y. Now divide everything by 2 to isolate the x, and we get x equals 8 minus y. Now substitute it into the other equation, xy equals 15, and we get y times 8 minus y, which was x, equals 15. Distribute it, and we get 8y minus y squared equals 15. This is now a quadratic equation, and we can subtract 15 from each side to bring it into standard quadratic form, ultimately getting negative y squared plus 8y minus 15. Now we can solve the equation using the quadratic formula. And the solutions we get are y equals 3 or y equals 5. If y is 3, then 2x plus 2y equals 16 means that 2x plus 6 equals 16. Subtract 6 from each side, then divide by 2, and x equals 5. If y is 5, then since 2x plus 2y equals 16, it means 2x plus 10 equals 16, and subtract 10 from each side, 2x equals 6, which makes x equals 3. Therefore, our two solutions are x equals 3 and y equals 5, and the other one is x equals 5 and y equals 3. Or in graphing form, 3, 5, and 5, 3. Since x is one dimension and y is the other dimension, it means it's 3 by 5 either way, either 3 width and 5 length, or 5 width and 3 length. Again, ultimately it doesn't matter. It's the same rectangle, just a question of rotation. In the next class, we are going to discuss logarithms.